Today we're actually going to start solving systems using some of that theory that we talked about with matrices. Okay, so here's how we'll start. I'm going to refer back to that one example that we kept talking about in the previous section, which was dx dt equals x plus 3y, dy dt equals 5x plus 3y, and we showed that the solution was something like this: c1, 1, negative 1, e to the negative 2t, plus c2, 3, 5, e to the 6t, where x represented the column vector x and y. Okay, so what we're going to work with is maybe the hypothesis that since both of the solution vectors had an exponential function, that maybe this is the case always. So we'll see what happens. Since both solution vectors have the form x, let's do x sub I, equal to k1, k2, e to the lambda I t, maybe this is always the case. So is this always true? And the systems that we were studying, I mean, here's the example that we referred to earlier, but of course we're talking about for the system x prime equal to ax. Okay, so if we start with just this equation here in general, okay, and let's go ahead and take the derivative. So what we'll do is, let's kind of rewrite this solution vector as a column vector, k, e to the lambda t. Okay, so if this is the general form for x, and this is the system that we're starting with, we'll go ahead and take the derivative of x and see if we can arrive at some conclusions here. So the derivative of x will be that same column vector k times lambda times e to the lambda t. And now this has to equal a times the original column vector x. Which is the same as a times k e to the lambda t. So now if we cross out the exponentials on both sides, we get that a times k has to equal lambda times k. Well, this should look familiar if you remember what we did in the last section. I believe what we did was move everything to one side. And then we multiply the identity matrix with K. Factored out the A minus lambda I. So factored out the K, that was what we had left. And we determined that K could not be 0, which then meant that the determinant of A minus lambda I had to equal 0. Because that was the only way we'd be able to get rid of it, or not be able to get rid of it. In other words, non-invertible and this is what led us to using the whole eigenvectors and eigenvalues, and now we're going to tie that into here. So since we basically come up from x prime equal to ax, we arrive at the same condition, we've basically shown that x equals k times e to the lambda t will be a solution of x prime equal to ax if and only if lambda is an eigenvalue of A. And obviously k is an eigenvector corresponding to lambda. So it wasn't just to do all that matrix work. It all had a purpose. And here it is. First, we'll go through the distinct case. Okay, so we'll see if we can get through all the distinct cases today. And then there's also the case where we have repeated eigenvalues, which is not too bad, but that's probably what we'll finish with next time. Right, so let's say we have n distinct eigenvalues, lambda 1 through lambda n. And we'll make sure that these are real to start. Of the coefficient matrix A in the equation x prime equal to ax. Let's also let k1, k2, and so on, we'll let these column vectors be the corresponding eigenvectors then the general solution now that we know what they're going to look like, using the superposition principle, will be C1 K1 e to the lambda 1t plus C2 K, whoops, that's not what I meant to do, plus C2 K2 e to the lambda 2t and so on, down to c sub n, k sub n, e to the lambda sub n t. Okay, so we're going to use a superposition principle, combining all our vector answers, and we'll be done with it. Okay, so we'll work through one example together, then I'll give you one to try on your own, and we'll see where we're at after that. Okay, so let's say we have the system x prime equals 2x plus 3y, y prime equals 2x plus y. Okay, so first, identify that well, this is really the same thing as x prime equals ax, where A is the coefficient matrix 2, 3, 2, 1. Okay. So first what we're going to do is find the eigenvalues corresponding to the coefficient matrices of the system here. So first we do the determinant of A minus lambda times I. Set that equal to 0 and find our eigenvalues. So that'll be the determinant of 2 minus lambda, bless you, 3, 2, bless you again, 1 minus lambda, which gives us the polynomial lambda squared minus 3 lambda plus 2 minus 6, which is the same as lambda squared minus 3 lambda minus 4. So that gives us two distinct eigenvalues. Lambda 1 equals 4, and lambda 2 equals negative 1. Okay, so for lambda 1 equals 4, we're going to solve the augmented matrix A minus 4I with the 0 column vector. So take your A minus lambda I matrix and just plug in lambda equal to 4. So now we're going to get negative 2, 3, 2, negative 3. And you can do a whole bunch of row operations or kind of see it at this point. Multiply by negative a half. So after you add the rows together and multiply the top row by negative a half, we get the relationship that k1 has to equal 3/2 times k2. So the first eigenvector, we just have to pick values as long as k1 and k2 have this relationship. So I'll do k2 equal to 2, so then k1 would have to be 3. Okay, for lambda 2 equals negative 1, plug in lambda into your A minus lambda I matrix. We get 3, 3, 2, 2, whoops. And again, subtract the rows, multiply by a third, And you get that k1 has to equal minus k2. So my second eigenvector, I'll just pick k2 equal to 1. So then k1 would have to be negative 1. Okay, and you can have any eigenvectors you want, really, when I grade your exams, as long as this relationship and this relationship hold true. That's what I need to make sure you've done. Okay, so our general solution is going to be C1 times K1. So we have 3, 2, and then e to the lambda, so whatever the eigenvalue was there, which was 4, times t, plus C2, negative 1, 1, e to the negative t. And here's our general solution. And again, we know that x is our column vector representing x and y here. Okay? Now, back in 8.1, we solved these systems another way. So just make sure that you haven't forgotten that this is the same as writing x of t equals 3 times c1 e to the 4t minus c2 e to the negative t, and then y of t would have been 2c1 e to the 4t plus c2 e to the negative t. Okay, so in 8.1 we eliminated, and now we can use eigenvectors or eigenvalues, which makes life a little easier without having to do all that work that we did in the beginning of the unit. Okay? Are there any questions on how to actually solve the systems? Okay. Why don't you guys try this example? So here's a 3 by 3 system of linear differential equations. This will take you a few minutes, but let's see if we can work through it.